CHED Delta project, a portable waste energy recovery equipment system using plasma technology. The Plasma Technology Project is a CHED-funded research collaboration between Holy Angel University as the lead HEI and Don Honorio Ventura State University, partner HEI, under the Discovery Applied Research and Extension for Interdisciplinary Opportunities (DARE 2) research grant. The Plasma Project works on the development of a portable system that applies plasma technology to convert solid waste into renewable energy. Let's get to know the team behind this project. Team Plasma is led by Dr. Filipina I. de Guzman as the project leader, who's a chemical engineer. Engineer and Marie Mangiliman is a professional electronics engineer by profession and also the project coordinator for HAU. Engineer Gerard C. Cortez is a computer engineer and also the control system lead for HAU. Engineer Renato S. David is the plasma generation system lead and a civil engineer. Engineer Edwin S. Echo is the power system lead, who's a mechanical engineer. Engineer Jerome V. Lapitan is an electronics engineer and sensor system lead of the project. Engineer Cherian P. Navarro is the research documentation lead and also a professional electronics engineer. Engineer O.J. D. Santos is a registered electrical engineer and the electrical system lead for HAU. Engineer Maria Elena Y. Timbang is the Singas cleaning system lead and a professional industrial engineer. Engineer Ana Liza C. Nashin, who's an industrial engineer, and Engineer Alma L. Tangcuenco, an electrical engineer, are the team members from our partner HEI. What is the research project all about? This research project demonstrates the proof of concept of plasma-assisted gasification on municipal solid waste, an advanced waste treatment technology which has not yet been applied in the Philippines. The project involves the design and development of a waste processing technology, where practically all types of solid wastes may be broken down into elemental or synthesis gas and slag utilizing radiant energy from an electric arc in a closed vessel called a plasma reactor. The Singas may be used to generate steam that drives a turbine to produce electricity. In this project, the electricity produced is initially intended to be used in running the plasma reactor to further gasify waste and run the system in a sustainable. Let's take a look at the project design. The machine is composed of 4 system blocks. The first one is the plasma reactor and feeding system. This is composed of the plasma chamber and the waste shredding and conveying system. The produced Singas is fed to the power generating system. The next one is the power generating system. This block includes a boiler or heat transfer chamber, steam turbine and generator assembly, condenser and cooling tower. Steam that goes out of the turbine goes to the condenser and cooled by a cooling tower. The condensate is then directed to the water tank feeding the boiler with water. The third one is the Singas cleaning system. The cleaning tank, sprinkle tank and 10 horsepower induced dragged fan make up the Singas cleaning system. The draft fan induces out Singas immediately upon detection of an uncontrolled high pressure. In this block, Singas is sprayed with water to remove the particulates. The water is then conveyed to the cleansing tank and pumped back to the sprayer. The last one is the control system. This system works as the sensing unit of the machine and monitors the temperature and pressure inside all pressurized chamber. It switches off the power source of the system blocks once uncontrolled temperature and pressure are detected and activates the 10 horsepower suction pump when needed. Project development and accomplishments. Development of waste processing system. The original plan for the waste processing system is that a shedder will be attached to the accepting bin of the plasma reactor, whereby an oxygen sealing butterfly doors will reduce the oxygen intake of the system, but this has confronted the researchers with several challenges such as frequent waste clogging on both the shredder and doors, waste feeding dangers, etc. These challenges lead to the separation of the shredder from the accepting bin. A screw-type conveyor was designed and developed to create the oxygen intake reduction in lieu of the butterfly doors. It was firmly observed that the problem of clogging is due to the size of waste that was intended to be gasified with reference to the experiences of other countries. Development of plasma reactor system. The plasma reactor is functioning satisfactorily as it produces the desired temperature of at least 1500 degrees Celsius. Several experiments were performed to produce plasma inside the reactor, but the researchers had faced the following challenges. 1. Plasma torch. The energy consumption in producing a plasma torch is more than double compared to the other sources, not to mention the need for an inert gas that is necessary to deliver the torch inside the reactor because the air is prevented to enter the chamber. 2. Microwave plasma torch. Issues of temperature prevent the microwave plasma torch to function well, and the magnetron design does not fit the plasma reactor environment as it need to be inside the reactor, but it would not survive the extreme temperature inside it. 3. Plasma arc. This method was concluded to be the best way in producing plasma inside the reactor via the plasma arc generated by two graphite electrodes supplied with energy by a high voltage source. The plasma arc generation is up to a few minutes only, for it seems to be self-sustaining as waste act as fuel in the gasification process. Nonetheless, the different inquiry on the plasma torch generation procedures has made the researchers further understand plasma torch and plasma arc productions. Development of power generating system. The power generating system was designed and installed, but the researchers were not able to fully test its capacity, primarily because the conveying pipes from the plasma chamber to the boiler, which were made from 36 structural steel pipes, were not able to withstand the intense temperature of the flowing synthesis gas, thus preventing the heat transfer necessary to produce steam needed to drive the turbine generator assembly and produce power. A proposed correction was designed and planned, either replacing the conveying pipe with a much larger diameter pipe embedded with refractory material or move the chamber closer to the boiler, but was not executed due to the limited mobility brought about by the COVID pandemic. The findings in the experiments clearly manifested the conversion of the feedstock into a high-temperature synthesis gas. The high temperature can be sustained even when the plasma arc is no longer present inside the chamber. This led to the conclusion that it is better and practical to incorporate the heat exchanger inside the plasma reactor, as no regular conveying pipes material can withstand the passing synthesis gas temperature. Prototyping of portable equipment. With the series of meetings, planning and brainstorming with consultants, the whole equipment was conceptualized in detail and fabricated with the help of capable fabricating companies. Experiment guides and workbooks were presented and discussed. Actual experimentations ensued after details were confirmed and agreed. Waste handling procedures and the equipment were adjusted to cope up with the waste content and composition that is clogging seal doors and the shredder. Proper temperature protection was recommended to make equipment parts more resistant to melting. Equipment adjustments to improve procedures were recommended as per logical engineering solutions. Incorporation of further synthesis gas cleaning were recommended using twin bubbler system. Testing of portable equipment. The machine has 3 components, and each component has their separate line of tests to accomplish, which is the waste processing system component, the power generation system component, and synthesis gas cleaning system component. For the control system monitoring, the initial testing of machine components is done manually by attaching thermocouples interfaced with 2 and 16x4 LCD display via Arduino controller for the temperature reading. After the successful manual testing, the automated testing was conducted on the web-based application. The control system for monitoring the temperature and pressure on several components of the machine, especially the plasma chamber. It is being handled by the Raspberry Pi 3B and Arduino Uno hardware controllers. Real-time monitoring is done via a web-based application developed using HTML, CSS, PHP, Apache, and MySQL for the user interface. In the background, the server is implemented using Node.js architecture, and the database system using MongoDB platform. An improvised bubbling system was installed and found to be effective in capturing the water vapor. The synthesis gas was captured in test tubes where the flammability tests performed was observed to be inconclusive but promising. The team was confronted with the spreading of the COVID-19 virus, restricting movements, experiment times, group collaboration, work efforts, and access to all types of resources. Yet still, experiments were carried out to a controlled level, abiding by government guidelines and restrictions. Activities were continued even to the point of using personal resources in achieving crucial information. However, the team can only provide so much, and equipment adjustments that cannot be attained through improvised means were left untouched, limiting outputs to what were relayed in this report. It is imperative that the government should continue funding works of this scale and theme. The team would like to extend their special thanks to Dr. Ruby P. Hinson, former project leader and chemical professional industrial engineer, Dr. J.P. Paharalaga, former member mechanical engineer, Engineer Mervyn Gundren, former member mechanical engineer, consultants Rottles and Tongal, Felicito Caluyo, Ferdinand Manigday, Fernando, Francisco, Iraldo David, Magdaleno Vasquez, Melo Rutherford Mendez, Clerk Ms. Bianca Isabel Navarro, Technical Assistant Virgil Sinio, Nicole Bautista, Ariel Cabildo, Franklin Calleja.